Hey there, we are starting Newton's second law here. You've done a little bit of work with mass and weight, and now we're going to start talking about specific forces. In the beginning of this, hopefully you have already gone over this with Mr. Guerin. If not, let's stop and pause this, go through this reading so we understand the basics of what forces are, and we have that all filled out. We're going to jump down to the bottom here and take some notes on specific types of forces here. Okay, in general, a force, as you saw from your readings up there, is a push or a pull. Could be either one, a push or a pull, and we measure those forces in newtons. And the abbreviation for a newton is a capital N. So force is a push or a pull. It's measured in newtons with a capital N here. And there are several different types of forces that we're going to talk about as we move further into this second law that we are starting to look at here. So one of those forces is a friction force up here in the upper left. And if you take your hands and you rub them together and you feel that heat that occurs, that is an example of a friction force. A friction force occurs between two surfaces. So in the case that we just talked about, those surfaces are your hands. If you're pushing a book across the table or something like that, that would be the book and the table are the two surfaces that we're talking about there. A friction force acts in the opposite direction of motion. Friction force acts in the opposite direction of motion. Okay, so we're talking about pushing that book across the table. The friction force is slowing the book from moving in the direction that it wants to go. So there is one new force, and then let's switch over to one that we have already talked about, weight. Okay, remember we call that F of G because weight is the force of gravity on some mass. That, of course, if we are on Earth or even on other planets, acts on all objects all the time. Okay, that is why you are sitting down in your desk right now. That's why if you drop something, it falls to the ground. And again, that weight force is due to the gravity that we are all experiencing. So we already did a little work with Newton's second law because Newton's second law is F equals ma. When we're talking about weight, that is F of G, or our weight, is equal to ma. And remember, when we're talking about the a there, that acceleration is acceleration due to gravity, which is always, always, always 10 meters per second squared. And the last thing we want to know about that, which we probably already know, but we're going to write it down anyway, is that it always acts straight down. So when we draw this force, it will always be in this direction. Now, the opposite of that gravitational force, which is why you are not falling through the floor right now, is called a normal force. So our abbreviation for that is that capital F and then the capital N. And what this is it's a surface pushing up on an object. Surface is pushing up on the object. So right now, when you are sitting in your desk is actually pushing up on you, and the floor is pushing up on the desk. If it wasn't, we would all fall into the center of the earth, okay? Which, of course, we don't want that to happen. And then if we are moving right along here to our purple force here, That is a push or a pull. That's a force. That's something that we would apply on there, okay? So this is referred to as an applied force. So if I go back to talking about that book again, when I push that book, that is an applied force there. This acts in the direction of motion. So whichever way I want that book to move, that is how it's going to move, because that push force is acting in the direction of motion. And usually that's going to be left or right. We're going to start drawing some diagrams in just a minute, so that will make sense. And the last one is something you also probably have experience with, you understand a little bit, and that would be air resistance, okay? Air resistance is something that acts upward on falling objects. Acts upward on falling objects. So think about like a feather falling down, and you can see the air resistance kind of slowing it down as it moves toward the ground. Okay, so we'll leave that there for just a second. So if anybody needs to finish this up, and again, these notes will be posted later too. Just do your best to get them as we're going through. So we're going to scroll up now. We're going to talk about the net force. When we refer to the net force, what we're talking about is the sum or result of all of the forces acting on an object. So again, the sum or the result of all forces acting on an object. And that net force can either be 0, and that means that all your forces are balanced, and we're going to see what that looks like in just a minute. So if your net force is 0, all your forces are balanced, means there's something that is going in the opposite direction of all of them. And that is going to mean that your object is at rest or moving at a constant speed. So again, if net is 0, all your forces are balanced. So you could be at rest, just sitting there doing nothing, or moving at a constant speed. Everything is balanced out in that case. If your forces are not balanced, we're going to say your F net does not equal 0. And that, by definition, means that you have unbalanced forces. And when that is the case, the object will always accelerate. Okay, and remember, accelerate can mean that it's slowing down or speeding up, but you've got unbalanced forces, so your F net is not 0. Your object will accelerate in that case. Now, to show what's going to happen, whether it's at rest or at a constant speed or accelerating, we're going to draw what's called a free body diagram or a force body diagram. Either one is fine. It is going to show you all of the forces acting on an object. So there are 4 steps for drawing these. So let's write those down. The first is we are always going to draw all forces from the center. And even if these don't make sense right now, let's just write them down because we're going to do lots of examples here in just a minute. Draw forces from the center. And you are going to draw and label arrows with type of force. So we're we're going to use those types from up above. It'll be air resistance, it might be weight, might be a push or a pull, normal force, gravitational force. And then when we're done, we're going to decide based on our diagram. Oops, I got a little extra one in there. We are going to write down if the F net is equal to 0 or if the F net is not equal to 0. So we're to decide based on our diagram what that's going to be. And if your F net does not equal 0, we're going to have to show the direction of the motion. So we're just going to draw an arrow that says it's going up, down, left, or right. So again, when we're drawing force body diagrams or free body diagrams, forces always draw from the center. We label our arrows with the type of force we're talking about. When we're done, we decide if F of net is 0 or not 0. And if it's not 0, then we show the direction of motion. So let's do 4 examples here, and then you'll have lots more practice this as we go, okay? So first one, let's say that we have a box of Kleenex just sitting on the desk here. It is at rest on the table. If it is at rest on the table, this is the center of my object, and we have 2 forces that are acting on it, okay? One is always gravitational. So a down arrow with FG has to be on every one of your diagrams. And since that Kleenex box is not falling into the table and down into the center of the earth, there must be something pushing in an equal and opposite direction because it's not moving anywhere. And that would be, remember, what we call your normal force. So gravity's pulling the Kleenex box down, the normal force is pushing up. And if we look at that, and I did my best to make those arrows the same size, we will say F of net equals 0 because I knew it's at rest. That means it has balanced forces. Okay. In the next one, let's say I want to go ahead and I am going to push this Kleenex box to the left at a constant velocity. I'm just going to keep pushing it. I'm not going to let go. It is going to be a constant velocity. I'm pushing with the same amount of speed. If that is the case, I still start in the same place. There is still gravity acting on that Kleenex box. There is still a normal force pushing up on that Kleenex box. If that wasn't the case, then it would be either floating up in the air or falling down to the center of the earth, okay? Now, what happens here is I'm going to push it to the left, but anytime I push it to the left, there's an opposing force. Remember that opposing force of motion is friction. So FF there. But if I keep pushing that and I don't let go, my F of net is still equal to 0. I still have balanced forces in that case because I am continuing to push that Kleenex box. I'm not taking my hand off it. I'm continuing to move it in that direction. So there's your 2 with balanced forces. Now we're going to look at doing some different ones. We are going to move the Kleenex box to the right, but this time it's going to accelerate. So we're going to have a little bit different situation here. So again, everything from the center, everything experiences gravity, everything experiences a normal force. If it does not, it would be floating up above the ground or falling into the center of the earth, right? Now, if I want it to accelerate, what has to happen is I have to give this a really good push, an FP, and I said I was going to go to the right. There's still friction, but I have pushed that farther and harder in that direction, okay? So in this case, F net does not equal 0 because I have a longer arrow in the push direction. This is what's called an unbalanced force. So that is going to move in the other way. It's going to actually accelerate to the right. Okay, this longer arrow means that I have an unbalanced force. And then our last situation says the Kleenex box is going to accelerate to the ground. So like I would hold it above my head and I would drop it down to the ground. So if that is the case, this gravitational force is taking over, and this is not sitting on a surface anymore, so there's no surface pushing up, but this is the situation where I would have air resistance. Okay, but the gravitational pull is greater, that's why it's going to fall to the ground. So again, this is a situation where F net does not equal 0. There is an unbalanced force, which is why the Kleenex box accelerates to the ground. Okay, so we have some examples to look at there as we are going through there. You're going to have some homework. Don't worry about this so much. Just do the pages that you are assigned. Good luck with all this. And again, remember, there is a Schoology discussion post if you have questions for me. And you can email me now, and I will answer as I am able. Hope all's going well. See ya.